screencast, we're going to review feedback loops, a very, very important concept within biology. They're very important because feedback loops are what our body uses to maintain homeostasis. As we remember, homeostasis is the tendency of biological systems to maintain relatively constant internal conditions despite external changes. We do not live in a perfectly stable environment, and so there are things that are changing externally that are going to impact our body or internal conditions. These could be things within the environment or things that we actively do, like eating or drinking or exercising. There are certain things, certain variables that must stay within range in order to maintain homeostasis, in order to stay alive and to live healthily. This list is not an exhaustive list, but it does include some of the major ones. Things like pH, body temperature, blood sugar, blood oxygen levels, hydration, so our water levels, concentrations of different chemicals, hormones, elements, things like calcium, as well as even just something like toxicity, waste, right? We don't want waste to build up, and we produce waste all the time, whether it's through eating and drinking or just through breathing and moving around. Our body is producing waste that we need to get rid of in order to maintain homeostasis. So our body maintains homeostasis, and when I say our body, I mean all living things, but our bodies maintain homeostasis through the use of feedback loops. So a feedback loop is a system that's used to control a variable, and it can be either positive or negative, which we'll talk about in a little bit. Before we get into all the intricacies of a feedback loop, let's review some terms. So a variable is anything that changes. So any of these things that I listed that must stay in range, those are all variables. A set point is going to be a physiological value, so it's a set value around which a normal range is going to fluctuate. A normal range is a restricted set of values that is optimal for health and stability. So for example, we say that human body temperature is 98.6 degrees. This would be the set point. Now, that would be what would be considered the middle of our normal range, and our normal range is going to be all the temperatures around our set point that are still healthy and stable. So you wouldn't be too cold yet, you wouldn't be too hot yet. There's a range that you can fluctuate with for temperature and still be healthy and maintain homeostasis. Receptors or sensors or sensory receptors are going to detect changes in variables, things like temperature, pH, blood oxygen level, blood sugar, etc. The control center can be the central nervous system. It often is the central nervous system or the brain or a part of the brain. Some organs have their own control centers, but what's going to happen here is there's going to be an integration of sensory information. So it's going to collect all the sensory information, bring it together, compare it to the set point, make a decision based on that information and that comparison, and then tell the effectors what to do. The effectors are then going to make the change, and we know effectors to be things like glands or muscles. These can be skeletal muscles, smooth muscles, or cardiac muscles. Usually, with homeostasis, the effector is going to be a gland. So here's a generic feedback loop. You have some sort of variable. Okay? Again, this variable needs to stay within a certain range. It needs to stay close to its set point in order to maintain homeostasis. But again, we do not live in a perfectly controlled environment, and so something happens on the outside that's going to cause a change in this variable. Receptors are going to detect a change in the variable, and receptors are sensitive to specific variables. They're going to send this message to the control center. The control center is going to compare the information it just received to a reference value or a set point. It's going to then make a decision based off of this set point and what the current variable value is, and send a message to the effectors to change the variable. The effectors are then going to make that change, and something's going to happen to the variable. So A popular example here is thermal regulation. So let's say we have our body temperature, again, should be 98.6, stay in that range, but we have something outside of our body that causes our temperature to decrease. Perhaps we go outside and it's cold outside. So our body temperature is going to go down. The thermoreceptors, so thermo meaning temperature, are going to sense the temperature change and send that information to the control center. In this case, the control center is the hypothalamus. The hypothalamus is going to compare the current temperature to 98.6 degrees, the set point. It's too low, and so this is going to make the muscles shiver and the blood vessels constrict, both of which are going to increase body temperature, and so now the body temperature is a little bit warmer. Thermoreceptors still check the change, send it to the hypothalamus. If it's still too low, then the muscles are still going to shiver. The blood vessels are going to stay constricted until the body temperature raises, and the thermoreceptors say, okay, this is the new body temperature, compare it to the set point, and we're good. It can be the same thing going in the opposite direction. So perhaps something happens that makes our body temperature increase. Maybe we start exercising. So we're running around, we're producing heat within our body because of our muscles, and now our body temperature increases. Thermoreceptors detect that change, hypothalamus compares it to the set point, and we're going to do the opposite. In this case, our blood vessels are going to dilate and we're going to start sweating in order to release heat. Body temperature is going to decrease. And so this just keeps going around. Now, perhaps I am exercising, I'm sweating a lot, and I was running around inside a gym and it's basketball season, it's the middle of winter, and then I walk outside without a coat on, not smart, and because your body does not want that, you want to keep your muscles warm and make it be a little bit gradual, but the body temperature then gets too low. Well, now maybe we're going to do the opposite and we're going to start shivering and our blood vessels will constrict again. So a positive feedback loop. A positive feedback loop is not very common. There are very few examples in the human body. And so a positive feedback loop is when a change in the variable in whatever direction produces a response that increases that change. So it makes it go even further in the direction that it was already going. An example that is a hypothetical example is that if temperature increased, that feedback loop here would try to make your temperature increase even more. Now, that's not a real example because we want it to stay within a certain range, but that would be an example of a positive feedback loop. Some real positive feedback loops are oxytocin during pregnancy. So once you start contracting because you're ready to start having the baby, the oxytocin levels rise, which makes you produce even more oxytocin, which makes you contract more, which makes the contractions go faster and stronger. Milk production or lactation in nursing mothers, same thing. The production of milk stimulates more production of milk. Blood clotting. So when you have a cut and you start the blood clotting or the stopping of bleeding, that's actually going to trigger a cascade that makes you clot more and more until the bleeding is completely stopped. And the last one, not in humans, but is ethylene ripening in fruit. So this is why you have a banana on the counter or an avocado on the counter, and they're green and they're not ripe, and then all of a sudden they're super overripe. Because what happens is a little ethylene being released. Ethylene is in charge of ripening. So ethylene is released, which makes it ripen, which makes more ethylene produced, which makes it ripen even more. And so that is what happens with ethylene. So these are examples of positive feedback loops. However, most of the feedback loops within our body are negative feedback loops. Negative feedback loops cause a change is when negative feedback loops happen when a change in a variable produces a change or a response that reverses that change. So these are the examples that we've talked about before, in that temperature increases, your body responds to that by decreasing temperature so that the temperature goes down, right? So it goes in the opposite direction. Same thing, if your blood sugar is too high, we're going to try to lower the blood sugar. If oxygen levels are too high, we're going to lower oxygen levels, which sounds kind of weird, but it would just be something like not breathing as much so that you're not bringing in as much oxygen. So a negative feedback loop is when a change in a variable in a given direction produces a response that reverses that change, so it pushes it in the opposite direction in order to keep it within that normal range right around the set point. And again, most of the feedback loops in our bodies are negative feedback loops. So here are some examples. These are some of the ones I've already talked about, right? Increasing and decreasing body temperature, carbon dioxide concentration, and our rate of breathing. So our breathing rate is actually triggered more by carbon dioxide concentrations in our blood as opposed to oxygen levels. And one that I didn't mention would be if you have a low level of water in your blood, then your kidneys will retain the water so that we don't get rid of any more water, because we want to raise those water levels back. If we do not maintain homeostasis, we need to quickly work to restore that balance. If we don't restore that balance quickly, it can lead to disease, or it could even lead to death of the organism if the being out of homeostasis is prolonged. So that is a quick overview of feedback loops and why they're important to our body to maintain homeostasis.